Hello, you should be able to hear me now. Is it working? Does it seem to be working?
Yes, sir.
Okay, great. Thanks. Okay, let me pull up some windows. Okay. All right. Okay, so we're going to continue on. We're going to pick up where we left off from yesterday, on Monday. Okay, so first, let me ask: does anybody have any questions about anything that we did on Monday? Is there anybody have any outstanding questions? Something that hasn't been figured out? Anything? Okay. Well, I put a link to language 1, but we're not ready really to start language 1. Maybe by the end of today we can look at beginning of language 1. Right now I'm gonna click on this language 0 because we haven't finished talking about that. And your homework assignment is based on language 0. So I want to keep going through the details of language 0. Okay. And last lecture, these were the notes that we did. We talked about how this language describes trees. Okay, so the idea that this language describes trees like, well, actually the language is over here. Yeah, so this is a piece of code, but you can write that code in, you can turn that code into a tree and then write it in the tree language. And remember, I mentioned that that's actually a programming language called Lisp. This style of writing code is actually used in a programming language. Okay, so we've got this language of trees, and over here in the code in the folder, okay, we looked at this example here. Okay, this is what we were doing towards the end of class on Monday. Here's a tree, and we want to build it using the tree constructors. So we went through this is the tree class. It's got a constructor for instantiating trees, okay? And if we want to build this tree here, we start by instantiating that tree with 3 branches, okay? So this is the code. This is what it looks like. This instantiates that root with branches B, C, and D, and that's branch B, branch C, and branch D. That's using this constructor, which takes an element as the root, and it takes 0 or more trees. See, this is the Java syntax for saying this function takes a string parameter and then 0 or more tree parameters. Okay, so, and then each one of those tree parameters is built by a tree constructor. Okay, so this constructor builds the root, and it takes 3 new trees. The tree B needs a root and 2 subtrees. Notice that these take no, now this is using the tree constructor with 0. That's using 0 subtrees. Okay, so when we get to here, there's 0 subtrees and there's 0 subtrees, which gives us these 2 leaves, E and F. Okay, C, which is a subtree of A, is just a leaf by itself. Okay, then D has 1 subtree, D has 1 subtree, G, but G has 3 subtrees, H, I, and J, and H has 1 subtree. Okay, so there's a lot of code to build a tree. Okay, all right. So I wrote it. I wrote that line of code. This is actually 1 line of code. See, it has 1 semicolon at the end. It is 1 constructor call. These are all parameters nested inside of that 1 constructor call. So this is all of 1 line of code. Here it is with no character returns in it. So here's the line of code. Here I wrote it as a single line of code without any character returns. I just let it, which is very unreadable. Really, really, really unreadable that way. The indentation makes it more readable. And then this is a little bit nicer way to indent the same code. Yeah, here, let's see, can I fit? I'll do a little trick. I'll split my window. Okay. So there's the tree in the upper half. I split the window. There's the tree in the upper half, and there's this constructor here. Now notice that now there's the constructor call that calls A, okay? And instead of putting the constructor call to B on a separate line, I just put it right here in line, the B, and then B has its subtrees E and F, okay? So that's just all been compressed down here. So here's the B with its two subtrees. So yeah, it's notice that before that was spread out over one line for B, one line for C, one line for F. Now A, B, and E are all in the same line, but it's pretty readable. A has a left branch, which is this one, which has a left branch, which is this one. And then this is the right branch of this one. Then A has a second branch, C, that's this one. And then D has a branch G, and G has a branch H, and H has a subtree K. So that's all on one line because that's pretty readable. That this is just going D, G, H, K. D, G, H, K, yeah, it's pretty compact all in one line. And then G has a second branch, and J has and G has a third branch. Okay? So G has branches H, I, and J. So you can write it in a fairly compact way. People play games like this. People try to come up with clever ways to format code that looks like this. Clearly, that's unacceptable code. You know, to say, well, it's one line of code, so I should type it all out on one line is really unacceptable. And then, you know, what's the better way? This one took quite a few lines of code, and this is pretty more compact. And as I pointed out the other day, your homework assignments essentially do this in reverse. Your homework assignment is to take this tree and print it out. And if you print this tree out, you could print it out. That's called pretty printing. You could pretty print it in a format like this, or you could pretty print it in a more compact format like this. When you pretty print it, you don't put the constructors. You just print out the, well, I'll run it and you can see. There's what it looks like pretty printed. That pretty printing was equivalent to that pretty printing is equivalent to this constructor call. A has a B, which has an E and an F. Then A has a C. And then A also has a D. So you see B, C, and D are all kind of in line with each other because that's A is level 0, B, C, and D are level 1, E, F, G are level 3, level 0, level 1, level 3. Level 3 is an indentation level in the pretty printing, and that's true over here too. Level 3 is E, F, and G. If you look over here, E, F, and G are all indented the same level. So a level of the tree is a level of indentation, okay? Now, if you strip out all the new trees and you just put the roots, then you get what's called the pretty printing, okay? I wrote the pretty printer that does that and gave it to you. You have to write a pretty printer that does something a little bit more compact, okay? This one's going to do things in a little bit more compact way. So you have to write the slightly more compact pretty printer that prints this tree analogous to this way that I wrote the constructor calls for it. Okay. Okay. Now, writing code like this is a nightmare. Okay. People don't want to write code like this to build trees. So we can do a little trick in the Java language. And some languages actually have this trick built into them. That's going to be the next example in this folder. Okay, we're going to do a little trick that clean up. Okay, I just want to clean things up. I'm going to do a little trick to make this stuff easier to read. So example 2 is almost exactly the same thing as example 1. I want to build that tree. Okay, here's example 1 that wants to build this tree. And then example 2 wants to build the exact same tree. But what I'm going to do in example 2 is I'm going to write the tree in the tree language and then have Java code build the tree from that tree language string. Okay, what amounts to is essentially treating this as a tree literal. Okay, what I'm doing is I'm turning that string into a tree literal, saying, here's what the tree should look like. Now build a tree for me. So we want to write code that builds a tree from this literal expression of the tree, as opposed to building the tree by hand by saying the tree has that root, and that root has 3 subbranches, and that subbranch has 2 subbranches. Instead of building the tree by hand, I want to say, here's a nice way to write the tree in this tree language. Now, write code that translate the tree language into a tree data structure. Build the tree. Okay. JavaScript has this in this is what JSON is about. JSON is a language for describing structures like these. Okay. So, but in JavaScript JavaScript builds JSON objects from JSON strings for you automatically. Okay. Here we have a tree string and we want to build a tree object, but we have to write the code ourselves. We have to write the code that builds the tree from the tree representation. Okay, so this is very much like JSON. JSON is a language built into the JavaScript language. It's a language. This is the grammar for that language. Over here is, well, eventually, when we get more practice in grammars, we have this grammar. Oh, where did I go? Where did I put it? Oh, here's our grammar for the tree language. Here's the grammar for the JSON language. It's part of JavaScript. It's a subset of JavaScript language. So there's the grammar. And here's another way to describe the grammar. And when you type expressions using that language, you get JavaScript objects. Okay. If you write an expression, see, they don't have any examples here, or do they? There's a simple example. That literal gets turned into a JSON object. You type that into JavaScript program, and it builds an object for you. Okay, these are more examples. You type that literal, and it builds an object. And you could use this to build trees. Right now you can use it. You could use this to build trees. So you have these strings in the JavaScript language that when you type those strings, they build elaborate objects for you. Java doesn't have anything like that. The Java language, the only literal that's built into the Java language is the literal for arrays. In the Java language, the only literal data structure you can build is things like arrays, where you can do int array A equal left brace. Okay, that's a literal array. Okay, as opposed to doing int A equals new int 4 int A 0 equals 1, A 1 equals 2. See, this would be the long way of writing it out. If I didn't have that array literal, and I wanted to build that array, I'd have to build the empty array, then fill it up. Okay? So the array literal is real useful. The array literal lets you do things in a much fewer lines of code. The only literal that Java gives you is arrays. It doesn't have a literal for building any other data structure. Okay? JavaScript has a real rich language of data structure literals, and it's called JSON. It's called JavaScript Object Notation. JavaScript Object Notation. It's a language for describing complicated data structures. Okay? Which is a beautiful thing. It's one of the beauties of the JavaScript language. It's one of the few things it did really well. One of the few things that JavaScript did well was building a nice literal sub-language for describing objects. Okay, Java doesn't have, C++ doesn't have anything like that as far as I know. Java doesn't have anything like that. Okay, well, actually, C++ has two kinds of literals. It has array literals and it has strut literals. It does also have strut literals in C++. Okay, so C++ has array literals and strut literals, but Java only has array literals. Okay, so when you want to build something like this, there's just no shorthand. Yeah, if you want to build that data structure that represents this guy, you've got to write it out this long, complicated. This is one of the things that people complain about the Java language. It's it's one of the little things that it would be nice if they had designed some kind of way of describing certain not arbitrary data structure. Even JSON can't describe any data structure. There's a JSON describes a certain kind of data structure. It's very versatile, but it won't do anything. There are data structures in JavaScript that you can describe, that you can build, that can't be built by JSON. Okay. Whereas in Java, it'd be nice if they had something that would like let you do this. Okay. All right. But we can mimic it. We can mimic a JSON-like language. So that's what this does. Here's our language for trees, and then we're going to look at the code now for the build tree function that takes that string and builds the data structure. Okay, and this is going to be the basis for and this is going to become the basic building block of building interpreters and compilers. The ability to take a string and turn it into a data structure is the parsing step of an interpreter or a compiler. Okay, so this is the first step of how a interpreter or compiler works. The program in a programming language is just a string. I mean, look at this. This is just essentially a big long string. The way to think about a program like this is it's just one big long string stored in a file. It's a text file. Okay. Okay, so you should really think of it as one very big long string. It's a string that represents a Java program. The Java compiler, the first thing it's going to do is take this string and build a tree out of it that we're going to call the abstract syntax tree. That was what we talked about in this example the other day. Oh, that was this. That's a line of code. The Java compiler takes that line of code and builds that tree out of it, which is called the abstract syntax tree. And if the Java compiler doesn't write that string, it doesn't need that string. It lets you write Java in this string, and the Java compiler still builds that abstract syntax tree for you. Okay. We're going to work with these strings, which are a little bit easier to work with. We're going to work with these prefix strings, not these infix strings. And we're going to build the abstract syntax tree from these simpler strings, the tree language strings. Okay, so we're doing the first step of a compiler. Take a line of code and translate it into a tree. Take a line of code and translate it into a tree, data structure. Take a line of code and turn it into a tree data structure. Okay, In our case, that's this method called, whoops, that one. It's this method called build tree. Notice it's in a file called parse tree. Okay, so we go here, we look at the parse tree. Here's the file parse tree that holds the build tree method. Okay, now this is where things get a little bit tricky. There's a fair amount of code going on here. Notice that this is like 80 lines of code. Okay, this is the program that takes in a tree string and gives us back a tree data structure. So it takes in a string. It takes in a string that's in this language, the tree language. This program will take in a string called expression, takes in a string called expression, and it's going to return a tree data structure. So the function takes in an expression and returns a tree data structure. And it throws a couple different kinds of errors. There can, as we'll see, there could be parsing errors and there could be tokenizing errors. We're going to talk about tokenizing and parsing. So in the process of like this string can have syntax errors. Eventually what that amounts to is that you can make a mistake when you write these strings. So for example, I could write a tree string A, B, C. Oh, that's a mistake. It's unbalanced parentheses. It's missing the last closing parentheses. So that would be a syntax error. I could also do an error by putting too many closing parentheses. That's also a syntax error. Okay. Another syntax error would be something like this. Okay. You can't have a tree. You don't. If you want a tree with just one branch, you would write it like this. That's the tree with branch B. Okay. If you put parentheses around it, if you have parentheses around it, then there needs to be a subtree for it. So that is literally, that's a syntax error there. Okay. So somebody can pass to parse tree a string that's misformed, and then you're either going to get a tokenizing error or a parsing error. We'll see what are the difference between those. So it's possible that somebody gives you a bad string. So you should be able to notice that there's a bad string. So, unbalanced parentheses, too many parentheses, wrong kind of parentheses. Okay, you get there'll be different kinds of errors that people can make. Okay, you could have the parentheses just in the wrong. You could have the somebody kind of goofed up and wrote open parentheses A, C, open parentheses. Okay, that's a syntax error. Okay, so our program that takes in a string in the tree language and builds a tree has to account for the fact that the string in the tree language may have mistakes in it. So that's these parsing mistakes and tokenizing mistakes. Okay, now here's how this is going to work. Okay, a string in the tree language looks like this. Here's a tree. Okay, if you look at that now, that tree, I mean, if I draw a picture of that tree, that's the tree 1, 2, 3 at the root with a left branch and a right branch. And the left branch is 4, 5, 6, and the right branch is the number 7, 8, 9. Okay. Notice that the tree has got a node here, a node here, and a node here. This thing is a unit. That's a node. Okay. And this is another unit. That's a node. Okay. Notice that this left parentheses is not part of that unit. Okay. The left parentheses stands by itself. Same over here. Over here, those 4 characters in a row, those 5 characters in a row are 3 separate units. One unit is the 7, 8, 9. Then the first right parentheses is its own unit. This is its own unit, and this is its own unit. So even though there's 5 characters in a row here, there's 3, what we call them is tokens. There's 3 tokens there. Okay. Now this is a string with 1. This is a string with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 characters. So as a string, it's a string of length 16. Okay. This space is not really doing anything. In fact, I probably could go like that. See, you would still understand that that is the root of the tree, and then this begins its subtree. Now, this space is actually useful. If you get rid of that space, then you have a token 4, 5, 6, 7, 8, 9. So that space needs to stay there. But this space probably doesn't really need to be there. You could put a space there if you wanted. You could put a space there if you wanted. Some people like to put space in their code to make it easier to read. Okay, so this is a opening parentheses, a number, an opening parentheses, a number, a closing parentheses, and a closing parentheses. Notice that none of that changes what's down here. Whether I have that space in there or not, or that space there or not, or that space doesn't really matter. And also I can put some extra spaces on the end there, doesn't matter. I can put some extra spaces at the beginning there. Okay, those should be okay. Whoops. Okay, so the program that's going to build a tree, when it takes this string here, the first thing it wants to do is tokenize the string by breaking it up into the significant pieces of the string. So what the tokenizer returns is essentially an array of tokens. In this case, this guy should break up into the array of tokens, left paren, 1, 2, 3, 4, 5, 6, I'm sorry, another left paren, 4, 5, 6, 7, 8, 9, right paren, right paren. Those are the tokens in this string. Okay, that we do that as a separate step called tokenizing. Break the string up into the significant pieces of it. So that means that this parentheses has to be broken off from, yeah. Now, if I did this, that space now matters. Now that would be the root 12. That would make this look like this. There would be a tree with a root of 12, a left branch of 3, and then a right branch with that tree. Okay, so some spaces don't matter. Some spaces do matter. That space matters. This space doesn't really matter. This space matters. This space doesn't matter. So the tokenizer's actually got quite a bit of work to do. It's not a trivial thing to figure out which chunks belong together and which ones don't. Okay. Here's a famous example. What's that mean in Java? Anybody have a clue? What does that mean in Java? Here's an interview question for you. This is not an uncommon interview question. Find out, how well do you understand languages? Okay. What does X plus 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 Y mean?
If I had to guess, like I've never seen that before, but if I had to guess, I'd guess post increment on X and pre increment on Y.
Well, no, that would make no sense because that would be treating this plus in the middle as being two things.
Right, that's what. But like I said, only guess.
Okay, here's one. Okay, the question is, how do you tokenize it? Does it mean an X followed by a plus plus, followed by a plus, followed by a Y? Or does it mean an X followed by a plus, followed by a plus plus, followed by a Y? Or does it mean an X followed by a plus, followed by a plus, followed by a plus, followed by a y. These are all valid Java here. This thing can be tokenized 3 ways. One of these is the correct tokenization, and the other 2 are wrong. But they're all valid Javas here. Let me show you. Let's actually do this in Java. Tokenizing is an interesting topic. That's one of the things we talk about in this class is what does it mean to tokenize a language? Something's gone wrong. Okay, that took a long time. Okay, here's the Java visualizer. It lets me type Java code in and run them in a web browser. So it's real nice. It lets me run Java code in a web browser. So let me create an int x equal, say, 2, and an int y equal to 3. And then I'll do int z equal x plus 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 y. Okay, and I click visualize. Notice that compiled, and it runs. X is 2, y is 3, and z is 5. Okay, now if you go back over here, which one of those gives you 5? Let's do them. Let's like, what does this give you? One line of Java, interview question, 1 line of Java, 5 characters. How hard is this? What does this line here mean? Take the variable x. Do what? Speak up. Come on, try it. Just start talking. You have to, I'm not kidding you. People are going to give you this in your job interviews. You don't sit there mute in a job interview. You don't get the job.
Increment by 1.
What?
Increment by 1 or?
Well, no. Well, what is this? This is the value of the variable x. Okay, what's this do? Addition. Okay, let's see. Let's go with addition. If that one's addition, what's this one? I'll give you a hint. What's that do? What
Does it maybe subtraction?
Pardon me?
Subtraction?
No, it's not subtraction.
Does it increment x and then subtract?
There's no increment in that line of code. There's no increment in that line of code. What does this do?
I to the 3.
Pardon me?
3 plus minus 5 will be like
It does
that is negative 5.
3 plus what?
Negative 5.
Negative 5.
Number.
So that's not subtraction. This guy is what?
Sign.
It's not subtraction. It's a different operator. It's got a name. It's called?
Sign.
No, it's actually called negation.
Negation. Yeah.
Negation. It takes that number and negates it. Okay, so this is negating y. Well, what's the opposite of negating y? Just leaving it alone. In Java, that's -5, that's 5. The language is symmetric. If you can put a minus sign in front of a number, you should be able to put a plus sign in front of the number also. So -5 means the negation of 5, plus 5 means 5. Okay? So This is y. Then this is double negate. Yeah. See, think. What would this give you?
Plus 5.
Because it's the negation of the negation. To
Mhm.
negate. Yeah. It's not an increment operator because there's a space between them. So this is the negation of the negation of 5. So it gives you 5. This is the plus of the plus of y. So this is y. This thing parses as x plus y. Okay? And we'll see that. Let me go up here and put it in there. Let me do okay. Now let's watch it. Notice that I'm going to get different values for Z1 and Z2. Z1 is 5, Z2 is 6. Okay. Now, why did Z2 become 6? 3 plus 2 is 5. How did Z2 become 6?
Did it increment
Of
X?
the X.
Well, look. See, yeah, somebody incremented X. This line of code did an increment on X. So we're getting a bit of a hint of what's happening here. But this line of code was X plus Y. It was 3 plus 3 is 6. Okay. Let me reorder these. Okay. Now, here's another plus 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 y. Okay. So I took these 3 pluses and broke them up this way. I put 2 of them together and 1 of them by itself. These 2 together now do what?
Increment X?
Post increment X.
Yeah, post increment, yes.
Now this guy is what now?
Just
Just the
sum.
addition.
Addition. Yeah, not the plus operator, it's the addition operator. Okay, so this will be increment X, then add Y. On the other hand, I could do that. What does this line do?
X plus the pre-increment of Y.
Pre-increment of Y. Okay, and then the question is, which one is this guy? He's one of these 3.
Yeah.
Okay.
Appar-
All right, he's one of those 3. And if you run it, it's hard to tell because since we're modifying Y by these lines of code, you can't just look at what's up here to see which one this guy is. So it's a little bit tricky to figure out. Okay, I'll tell you, for this line here tokenizes as this one. And here's how JavaScript, Java, and C++ all work this way. It's something called, it's got a cute name, Maximum Munch. Okay. Here's what Maximal Munch. Here's how the tokenizer works. X is a token. Okay, by itself. Plus is a token by itself. But plus plus is a token by itself also. Plus 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 is not a token. There is no plus 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 token in JavaScript, in Java. So you back off and you take the largest token you can find, plus plus. So what it does is it says X is a token, but so is X plus plus. Since plus plus is a larger token than plus, I'm going to go with plus plus. That's see, you munch off the largest token you can. Okay, then that leaves this guy by himself, and that leaves this guy by himself. Okay, so the tokenizer goes across and says X plus, there's no token like that. X plus is not a valid variable name. Okay, so X token by itself. Plus, well, it could be a token, but so can plus plus, but plus 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 is not a token. So we back off to plus plus, that's the token. That leaves this guy, well, plus y is not a token. There is no plus y valid token in Java. So plus is a token, then y is a token. Okay? So it's called the maximal Munch principle. If you write this code, people will shoot you, but it is valid code. Okay? It's actually, because it parses correctly. It is this thing here. Okay? And notice that there was 3 ways to tokenize this guy, and Java has rules that Maximal Munch is a well-known idea. It's even got its own Wikipedia page. It's something to do. It's an idea that comes out of tokenizing, and they show you examples in here. Okay, but it's a well-known enough idea that it even has its own Wikipedia page. A better name for it is longest match. You match the longest possible. Okay, if you're starting here, you always match. You match the longest possible token, and in this case, out of x plus plus plus, out of 3 pluses in a row, the longest token you can get is post increment. Okay. Here's a question. Will that tokenize?
Oh, maybe the way I thought at first. Could that be
Well,
post?
okay. Well, okay.
Oh wait, that wouldn't make sense though. If it post incremented then pre-incremented, it wouldn't.
Post increment x.
Right, pre-increment y.
No, but that would not. Okay, if it.
Oh, that would just.
Here's a question though. If it tokenized it that way, it wouldn't make sense.
Correct.
Okay, but so because you wouldn't be doing anything with the 2. Yeah, see, they would be like that. It wouldn't make any sense. Is there a way to tokenize it that makes sense?
Just plus, just use it post increment x plus y.
Plus and then plus y.
Right.
Okay. I don't know if Java may not like this one. There is a tokenization of it that works. It would tokenize as post increment addition the positive y. I'm not even sure if Java will accept it. It didn't like it. Yeah, it felt that that's a little too ambiguous. Okay.
So can you put a 5th one in there then?
Yep. Because now it's not ambiguous.
Right.
How should this tokenize?
Post increment x added to pre-incremented y.
Yeah, because now, okay, let's see if it accepts it. Oh, didn't like it.
Didn't like it.
It didn't like it. It did make sense. At some point, the tokenizer gives up and says, I can't figure it. It's kind of funny. Tokenizing is actually tricky. Tokenizing is not a trivial matter in programming languages. So even though this one does have a legitimate tokenization, the compiler gave up on it. It should have been, okay, I'll tokenize it myself. Okay, now it's happy because I tokenized it. I made the decisions. Okay. If there's only now, and if there's 4, I could tokenize it this way. Now I made the tokenization, and that's valid. Their website's being slow today. Okay, see, it compiled. It was valid. Okay, but I had to tokenize it. There are many examples in C, especially in the C++ language, where if you're not careful, the tokenizer won't tokenize what you have to tokenize things yourself sometimes. There are cases in C++ and C like this where you have to do the tokenization. Like, the one we did earlier is famous for being, okay, that tokenizes. That tokenizes as plus plus added to y. Okay, so that one tokenizes. This one, won't, even though it could tokenize, the tokenizer gives up on it. What was the error message? semicolon expected. Well, that's a pretty weird error message. If you gave this to C++, it might give you a different error. It might actually say that the tokenizer had trouble with this because it doesn't know. It might tell you that it's the tokenizer that had trouble. I'll show you a famous example. This example was when you write generic code, you write things like a list of string, right? What if you want a list of lists of string? So it's a list of lists. Okay, so it's a list of lists. Okay, now get rid of that space because it doesn't really play any role, and get rid of that space. C++ used to choke on this. Anybody got to guess why C? Now it doesn't choke on it anymore. They finally took them years. They finally fixed it, but the C compilers would choke on this. Anybody see something funny in there?
Oh, you just said sting, not string. Is that what you're talking
Oh,
about?
no, that's just me misspelling things.
Oh, okay. No.
Yeah. C++ compiler would choke on that. It would not be able to tokenize it. Well, actually, it would tokenize it. It would tokenize it stupidly.
Oh, is that like output or input or
Yeah, yeah. And it's also the shift operator.
shift? There, oh
Yeah.
yeah, the bit shifts. Bit
Yeah.
shifts.
Yeah. The tokenizer would say shift operator. And you would have to put a space there to get your code to compile. Java never had that problem, but C++ did for years. It couldn't tokenize that. You know, it would just say that that's the shift operator, and it would give it the wrong token, and it wouldn't token it. They would not tokenize it as closing of a generic operator, closing of a generic operator. Okay, it tokenized it as shift operator, so that put a shift operator after the word string, and you get a compiler error because the tokenizer couldn't figure out what was going on, and the solution was to put a space there. A lot of people still to this day would write that this way to kind of like avoid the having the greater than there. Java never had that problem, but C++ did. Tokenizing's tricky, okay? So now, when you want to build a tree, first you have to take the input expression and convert it into what we call a token stream. Convert it into the appropriate set of tokens. Okay, so like this would become this set of tokens. And then if you got rid, remember, if you got rid of that space, then it would become this set of tokens. Okay. Then the tokens are what we work with. We work with the token after the characters have been grouped into tokens. We then work with the tokens from then on. Okay. So this string, which is an array of characters, becomes this array of tokens. That's what the tokenizer does. It converts an array of char into their proper, essentially you might call grouping. It'll get rid of the superfluous tokens, like the spaces. They'll just be dropped from the token stream. So there won't be, these guys will disappear, this disappears, this disappears, these disappear, these will disappear, the spaces disappear, and then you get the significant tokens. Left paren 123, left paren 456, 189, close paren, close paren. Okay, so that's the first step over here. Now the tokenizer is written here. I'm not going to probably spend any time. We'll just accept that the tokenizer works okay. If you want, you can go look at it. This tokenizer, I got it from, remember, we have this, in the syllabus, I mentioned this one textbook, Crafting Interpreters. Okay, The tokenizer we're using is the tokenizer from this book. Okay, so you go start reading. He calls it scanning. Half the world calls it tokenizing, and half the world calls it scanning. So here's where he describes the tokenizer. See, he talks about tokens here. Okay, so I basically rewrote his tokenizer a little bit to make it work. I rewrote it a little bit, but essentially the tokenizer in our code, the tokenizer in this folder is the tokenizer from that book. Okay, so you can read that chapter if you're interested in this. Right now we're gonna accept that the tokenizer works. Okay, I don't really want to spend much time. You can write literally hundreds of pages on tokenizing. There are books that literally have hundreds of pages written about tokenizing. Tokenizing complex languages like C++ is very difficult. That's why I told you the story that C++ actually had a time when it couldn't even tokenize this thing here. That, you know, the C++ compilers were having so much trouble tokenizing this thing that they just told people, you tokenize it, you put the space there. Okay, right? So tokenizing is hard. So we're just gonna, you can read about the tokenizer here. He's got a nice explanation of it. You know, he's got a nice explanation of the tokenizing. Okay, and I modified his tokenizing code to be this tokenizer. Okay. Okay, so after you've tokenized it, now you have essentially an array of significant entities that you want to understand. So, for example, so this string has been boiled down to this list of significant tokens. Okay, so open brace means we're starting a tree. That's the root of the tree. Another open brace. Oh, notice that the tokens here are the things that are actually in the tree language. See, the tree language was a language of token, token, then more trees, followed by a closing token. So these are there's the opening token, a token that represents the root of the tree, trees, followed by a closing token. Okay, so now after the tokenizing, we basically have, if you want, now you can think of this, another way to think about this is after the tokenizing, you have something that looks like this. The left paren, the 123, the left paren, the 456, the 789, the right paren, and the right paren. So you can think of it as either way, as you've kind of cleaned this up so that you could see which are the distinct tokens, or you can think of it as a list of tokens. Okay, but the thing is, it matches the language better. This thing doesn't say anything about trailing spaces between. Notice that this grammar doesn't say whether there is or isn't a space between this guy and this guy. Notice that I put a space there for readability, but you're not required to put a space between the parentheses and the token. Okay, so this language is not saying anything about white space. Okay, so it could be that there's really no space between that token and that token. The grammar doesn't say that. The grammar doesn't spell out what's in between these things. Okay, so the tokenizing step, you can think of it as either converting this array of characters into an array of tokens, or you can just kind of think of it as simplifying the original string. It broke this up. It got rid of the superfluous what. Well, it essentially gave it to you as token space, token space, token space, token space, token space, token space, token. Okay, so it kind of simplified it. The correct way to think about it is this: it's an array of tokens. Though some people like to think of it as having given us this. What it really is, it took an array of chars and gave us back an array of tokens. Okay, then we work with that array of tokens. Okay, so given the array of tokens, we now build a tree from the array of tokens. Okay, now here's the build tree function. Okay, it takes in the array of tokens. Okay, what it does is actually it punts to another method. I wrote this as kind of in two steps. Build tree, is going to call getTree. Okay, and we'll see later why I wrote it this way. But in a sense, I have build tree called getTree, and getTree is the thing that really builds the tree. Now notice that after you've built the tree, building the tree should consume all the tokens. If there's any tokens left, you've got a problem. So for example, that would be something like this. Suppose there was an extra close parentheses there, which would put an extra close parentheses there, which would put a extra close parentheses there. The get tree would read up to here and say, there's a valid tree, and it would get that. We'll see that the way it works is it consumes a tree from opening to balance closing parentheses. So get tree gets that tree. But then there's something stray left over. So over here in the build tree, after you've got a tree out of the token stream, there should not be any tokens left over. If there is, you've got what we call a parse error. Okay, so this guy gets one tree from the token stream. The token stream should contain exactly one tree. Now, eventually, this is going to be called recursively. The reason I really have this guy called this guy, because this guy is going to be recursive. Because in the process of building this tree, it's going to have to build this subtree. So get tree is going to be the thing that gets one tree. In fact, it might have been, I could have called it get one tree. Okay, I could have called this get one tree. Usually, there's a lot of patterns to this. So get tree is a very traditional name to give this function. It gets one thing out of the token stream. And usually people don't say get one tree, they just say get tree. But it gets a tree, in our case, it gets a tree from the opening brace to its balanced closing brace. And in the case of if we're working with the original string, the string should hold one tree. It's not supposed to hold two trees, it's supposed to hold one tree. Now that tree can hold subtrees inside of itself. So get tree will call itself recursive, you'll see in a minute. But after you call at the top level, after you call get tree once, there shouldn't be any tokens left. Okay, now what does get tree do? Get tree is supposed to build a tree object. So here it declares a variable result. That's the tree it's building. First of all, it checks. What if this tree thing is empty? What if there are no tokens? Well, I've got a problem. If you ask me to build a tree from these tokens and there are no tokens, so here, tokens does has tokens is false. So if it's false that there's any tokens, I've got an error. So the first thing I do is I check to see, are there any tokens to parse? Okay, if there aren't any tokens to parse, I've got a problem. Okay, so check that there are tokens. Okay, if there is a token, get it. Okay, now hopefully what we got was a left parentheses. If we're starting to build a tree, the first thing we should get is a left parentheses token. So we go back over here and we get the token and we check, is it a left parentheses? If it isn't, that's another error. So if it is a left parentheses, that's okay. Down here is the else. Well, oh, I'm sorry. If it's not a left parentheses, it could be we treat it as a string. See, a tree begins with left parentheses or string. So if it's not left parentheses, then we're assuming that the tree is just a single root. Okay, so over here, when we grab the first token, we check that it's a left parentheses. If it's a left parentheses, we're building a tree with sub-branches. Otherwise, we're building a tree with just one root, a tree that's a leaf. Okay, so if we found a left parentheses, we're building a tree. If we find anything else, we're building a tree with just a single root. Okay, all right. Now, what if we found a left parentheses? Okay, well, now this code is kind of messy because you have to keep checking for things that could go wrong. What if you have a left parentheses and there's nothing after it? You know, what if somebody gives you a string and says, tokenize this guy? Here's my tree. Well, yeah, you got to account for that error. You know, they gave you an opening parentheses with nothing after it. So you have to keep, this code is messy because it constantly has to say, I've got things good so far. Now I have to make sure the next thing makes sense. Then the next thing makes sense, and I have to make sure the next thing makes sense. So it constantly has to stop and ask, is there a mistake? So after you get the left parentheses, you have to check, are there more tokens? If there aren't any more tokens, throw an error. Okay. If there are tokens, you build a tree with the next token as the root. Okay. So if you go to the language, what that's saying is, if you found this guy, so you found this guy, you found this guy, so go ahead and build a tree with this root, and then we'll add to that tree its sub-branches. So what we do now is we found the opening paren, we found the token that represents the root, we go ahead and build a tree with that root, and we'll then be adding sub-branches to that tree as we parse more stuff. Okay, so we found the left parentheses, there are more tokens, we get the next token and put it in the root of a tree, and now we're going to start adding subtrees. Now, how do I add a subtree? By recursively calling getTree. Here's the recursion in my function that comes from the recursion in this grammar. This is the beauty of this. This is the beauty. This is the part where you have where the grammar and the recursive grammar becomes a recursive function in my Java language. Okay. GetTree is parsing this thing here. It finds a left parentheses, so it's not in this case, so it's in this case, finds the left parentheses, finds the root. Okay, now it needs to get more trees. Okay, so the code is check the F tokens. If you don't have tokens, you can't do anything. Grab the first token, check that it's a left parentheses. If it's a left parentheses, you're building a tree. If it's not left parentheses, you're building a leaf. Okay. If it is a left parentheses and you're building a tree, well, check for more tokens, because if there's no more tokens, you got a problem. You have to throw an error. If there are tokens, grab that token and build the tree with that root. Now you got to start building more trees. You build more trees by calling add subtree get tree recursively with the remaining tokens. Okay. Now this gets one tree, right? There could be one or more trees here. See, this is one or more trees. Okay, so getTree gets one of those trees. There may or may not be more of those trees. So after you return from getTree, you need to know, are there more trees? Well, if there are no more tokens, you've got a problem. There has to be more tokens, because even if there's not more trees, there's this guy left. So after you get one tree, you check to see if there's more tokens. If there's no more tokens, you've got a problem. So there's an error. There should be at least one more token, the closing parentheses. Okay, so you check, you check if there's more tokens. If there's no more tokens, throw an error. If there is a token, you peek at it. You want to know, is it a closing parentheses or not? Because here in the grammar, what's true is after you've got one tree, the next token could either be a left parentheses, meaning that you're building a new tree. It could be a right parentheses, meaning you're closing the current tree. Or it could be a string, meaning the next tree is just a single root. Yeah, it could be like this. You've got an open parentheses, A. Then you've got an open parentheses, B, C, close parentheses. That was the first tree here. Now the second tree could be another tree or a root by itself. Then maybe another tree. Then maybe a root by itself, close. See, so the sequence looks like this. find the root, find a subtree, consume the subtree, check if there's anything left. If the next thing is a left parentheses, you're consuming a tree. If it's just not a token that's not a left parentheses, you're building a root, you're building a leaf. So this builds a leaf, this builds a subtree, this builds a leaf, and finally I'm done when I see the right parentheses. So the parse tree thing has to go through the possibilities here. The plus this, each of these trees can either be a left parentheses or a string. See, sometimes they begin with left parentheses and they're a whole tree. They begin with a left parentheses and they're a whole tree. Sometimes they're just a string by itself. They're just a root by itself. So I have to have some code that does that. Okay. So I peek at the next token. While it's not a closing parentheses, okay? So as long as I don't have this guy, I'm either doing one of these guys or one of these guys. I'm either doing a subtree or a leaf, okay? So while I do not have a right parentheses, now I'm going to just call add subtree recursively. And I'll let add subtree figure out whether it's in the case of a root, of a subtree or a root. In fact, the elegant thing is that the get tree is smart enough to figure out whether it's doing this case or this case. Okay, so I've got a while loop that says while the next token is not a closing parentheses, add a subtree to my current result. And if I ever run out of tokens, I've got a problem, because I should not run out of tokens before I find that closing parentheses. Okay, so it's a little bit tricky code. Look ahead at peek at the next token, make sure it's not if it's not a right parentheses, consume a tree, make sure there are more tokens. If there are more tokens, get it. Loop up here, make sure it's not closing the tree. If it's not closing the tree, add another subtree. Check if there's more tokens. If there aren't any more tokens and you haven't hit the closed parentheses yet, you've got a problem. If there are tokens, grab it. If you finally found the closed parentheses, you drop out of that loop. Oh, now here, this is actually a little bit redundant here. This thing only peeked at the code. Okay, see, it was peeking. So what peeking means, let me look at the token without removing it from the token array. So I'm only peek because I want to just know what's there. I don't want to remove it. I'm going to let subtree, I'm going to let get tree remove the tokens from the stream. So at this level, I'm just peeking at them, and I'm going to let this guy remove them. Well, when I finally find the closed parentheses, it's never been removed because it was only peeked at. So this guy removes them. It's called match. It removes the right parentheses. Okay. So that is a parser. Okay. So what we just looked at is the code for parsing this tree language here. Notice that 2 lines of grammar turn into, well, 2 lines of grammar are 40 lines of code. Okay, 2 lines of a grammar turn into 40 lines of code. It takes 40 lines of code to parse those 2 lines of grammar. What's most of the code? The error checking. Probably more than half that code, because look, every time there's an error, you have to throw an exception. And when I throw an exception, I put some little information in there about what token number I'm at, so that you can find. Remember, when compilers give you error messages, they point to where the error is. So when you're parsing something, you should be able to say, at the 27th character, that's where I found a problem. So when you throw this parse exception, you have to say what token you were at. Where was the problem? Okay. So see, there's 3 lines of code reporting an error, 3 more lines of code reporting an error, and actually this line of code is checking for the error. So you can see that the error, this is typical of real programming. The error checking is more logic than you've got the logic of what you want to do, and then there's the logic of the error checking. And it's not unusual for the logic of the error checking to swamp the logic of what you're doing, okay? If I took out all the error checking, I could parse that I could parse these 2 lines of grammar in half this much space, okay? Yeah, and actually, it's almost a good thing to do is to rewrite this without the error checking, where you assume that you're only given strings that are grammatically correct. So you assume, oh, no one's ever going to make a mistake. Always give me strings that are grammatically correct. Let me parse them. It's actually a good exercise to do that, so that you can see the pure logic of the parser without the error checking. Right now, this is the logic of the parsing mixed with all the error checking, and it gets quite a bit more messy. Actually, I think it's more than half this line of code is the error checking. Okay, like this, like all that's error checking. That's all error checking. That's all error checking. Yeah, at least half the code is error checking. Okay, and it's a nice exercise to take this code and say, let's just assume that the strings are always perfect. We don't ever have to worry about an error. What's the minimal logic it takes to parse the string, to build what's the minimal logic it takes to build a tree from the tokens, okay? All right, so we go back over here, and we now have been able to, we took this tree, and instead of building it by hand this way, we now say, well, here's the string that represents that tree. Let's let our logic build the tree for us from that string. Let's let our parser build the tree from that string. The rest of this program is exactly the same as this one. See, here's what you do with the tree after you built it. Well, all this code here is exactly the same as all this code here. What we're going to do with the tree after we build it is exactly the same. Once we built the tree, we don't care who built it. Here, we built it ourselves 3 times by hand. You know, I notice that I just keep redeclaring this variable. So I just show you that I can build the tree 3 different ways. I can write that one line of code. I can write that one line of code 3 different ways. Okay, but once I built the tree, I don't really care how it was built. So here, I build the tree by parsing a string, by parsing this piece of grammar here, okay? And the next example in that folder just does a bunch of strings. See, it's just what it's gonna do is gonna build an array of strings and then just parse them one at a time. So it's gonna loop through that array of strings and it's just a way of doing a whole bunch of examples. Okay? So it's just gonna build that tree, then build that tree, then build that tree. Okay. Now, when it does this, if I run this, if I compile it and run it, it shows me my trees in the output window. There's the first tree expression. There's what it looks like pretty printed. There's the second tree expression. That's what it looks like with the basic bare bones pretty printer. Remember, your homework assignment is to write a better pretty printer. Okay, so now at the same time this program is printing the trees out here, it's using that graph viz to build pictures of the trees. This tree here is this tree here. A is the root, B, C, D, E are the children, okay? The next tree is this one. A has 2 children, B and E. B has children C and D, and E has children F and G, okay? The next tree, graph viz, see graph viz draws these nice pictures for us, okay? So here's number 2, there's the tree expression, there's what the pretty printer makes it look like, and this is what graph viz can do for us. Writing graph viz is a lot of work. Graph viz is a famous program. Taking these, it takes, well, graph viz doesn't take these tree expressions GraphViz has got its own language. And what it's really doing is it's, see this file here, okay, we're doing this example here. What it really does is I wrote a program that walks the tree structure and writes what's called a dot file. And the dot file this is what a dot file looks like. See, GraphViz has its own language. What I need to do is translate from my data structure to GraphViz's representation. See, we have our representation of a tree, very simple. GraphViz has its own language for representing trees. It's more complex because it has to describe more. It's got to do things like, well, it's got to tell you what are nodes and what are edges and things like that. So I wrote a program that takes this tree data structure and translates it into this language, the dot language. Then that dot language file is sent to, that dot language file gets sent to GraphViz, and GraphViz draws the picture. Okay, and the code for that, just last show you, the code for that's in the program if you want to look at it. It's this tree to dot. Tree to dot converts a tree data structure into a dot file. They call their language dot. I have no idea why, but the language that GraphViz uses is called the dot language. So I'm translating from tree data structures to the dot language. Okay, and that's this code here. There's not very much code. It doesn't take much work to translate a tree data structure into a dot file. Okay, it's interesting stuff. I mean, you're seeing code at a fairly sophisticated high level. You know, this is real parsing of real languages. You know, well, a very simple. I mean, this is a baby language. This language here is a baby language, but we're doing, you know, it's still fairly tricky code. It's fairly sophisticated code, and we're doing things like translating from one language, our tree language, into another language, the dot language, and then the dot program can take the dot language and draw these nice pictures for us. Okay, we're doing language processing, which is what we want to get at. You know, that's what this course is about, is absorbing the idea of how you can go between languages and data structures. Go from language to data structure, from data structure to another language. Okay, I went from language to data structure, from data structure to another language, like a compiler. It's essentially, I've written a little baby compiler. I've compiled this language into dot. Literally, I mean, if I want to think of it that way, I've written a compiler that compiles from our tree language into the dot language, because I took the tree language, built a data structure out of it, read that data structure, wrote it out in another language. Essentially, I've written a baby compiler. Okay, well, we've run out of time, so we're going to quit there. Okay, if you read this code, it'll help you understand what you need to do in the homework assignment. So follow your nose through this code. You know, the entry point is one of these examples. You know, the entry point is one of these examples, and then you just say, okay, there's a string. I need to build. I need to read that because I'm going to build a tree from the tree language. You read build tree, and you kind of just keep following your nose. When you get to build tree, where is it? When you get to build tree, you see that the first thing it does is call the tokenizer. Okay, so you know, you can then look at the tokenizer code, you know, or you can assume that you can just take it for granted the tokenizer works, but you can look at the tokenizer code. Okay, then after the build tree does the tokenizer, then build tree calls this function build tree. Build tree calls get tree, and you just start, you know, you kind of follow your nose through the logic and try to absorb the idea. And the reading assignments give you background information on this. Okay. Yeah. These, you know, what we're doing is described in these reading assignments. Okay, recursive description of patterns. Okay, this is talking about grammar and turning grammars into trees. Okay, so they talk in here about turning grammars into trees. Okay, so it's tricky. It's not trivial stuff. It's very non-trivial stuff. So we're going to keep, we're going to spend the whole semester. We've actually talked about all the ideas of the semester. We're just going to add more details to them. But take strings, parse them into trees, process the trees. That's the moral of the whole semester. Take strings, build trees, process the trees. That's what a compiler does. Okay. Okay, and we've run out of time, so I'm going to go ahead and quit here. Let's see. We don't meet on Monday. Monday is Martin Luther King Day, so we don't meet again until a week from today. Okay. So remember, there is no class on Monday. We'll meet again in 1 week. Okay. And if you have questions about the homework, please send me email. Make sure you start working on the homework. It's not trivial. It's not a trivial assignment. Don't think you can do it in one evening. So start looking at the homework assignment. Okay. So I'm going to quit right now. Send me email if you have questions, and we'll meet again. Remember, 1 week from today. Have a nice weekend. Bye.